So today we have a question that has piqued my interest. This question is from J Advanced 2016 and it has piqued my interest since it covers and enraptures most of the topics from the chapter Thermal Properties of Matter. So let us now solve it. The ends Q and R of two thin wires PQ and RS are soldered and joined together. Initially, each of the wires has a length of 1 meter at 10 degrees centigrade. Now the end P is maintained at 10 degrees centigrade, while the end S is heated and maintained at 400 degrees centigrade. The system is thermally insulated from its surroundings. If the thermal conductivity of wire, which is given to us, we have to find the change in length of wire PQ. So firstly, we can see that this question is involving both heat transfer as well as thermal expansion. Since the thermal expansion, the linear thermal expansion part will have to be integrated clearly, as PQ is firstly changing its temperature, so we'll have to find out the junction temperature and then integrate our way to find the linear expansion in PQ. So let us now start by first finding the junction temperature. As we know, first let us draw the diagram. Let this be wire PQ. We've been given that they both have lengths 1 meter. PQ. So let the thermal conductivity be 2K. Since we have been given that conductivity of wire PQ is twice that of wire RS, let this be 2K, let this be K, let this be RS. So since we know from the junction law for thermal that we can absolutely apply nodal analysis to this, and in nodal analysis we can observe that firstly that also the temperature for S is given to be maintained at 400 degrees Celsius, while the end at P is maintained at 10 degrees Celsius. So we'll do that too. Then from nodal analysis we know that 400, let this junction temperature be T. 400 minus T over the resistance. We know that thermal resistance is calculated as K by LA. In general terms, where A is area of cross section, L is length of the resistive material, and K is the conductivity, thermal conductivity of wire. So here we'll have, so as we know from nodal analysis, this is essentially the voltage difference, and this is like in analogy with voltage, 400 minus T. So we'll proceed 400 minus T upon K by, since this is K and the length is 1, let the area be A. Then T minus, since also we know that 400 is the greater temperature, I have put 400 before T, since heat won't travel if T is greater than 400 degrees centigrade to the 10 degrees centigrade, then T would distribute. That's a separate problem in itself. Then T minus 10 upon 2K by here I have made a mistake. This will be L by Ka, and this will be L by Ka, and this will be L by 2Ka. Now we have 400 minus T by L by Ka equals T minus 10 upon L by 2Ka. Since the thermal conductivity for this rod with the T and 10 difference is 2K, we'll cut this off. This 2 will go over here. So 2T minus 20 equals 400 minus T. This T will go be transposed over there. 3T equals 420. T equals 140 degrees. So we've essentially solved 1/3 of the question here. We found the value of the junction temperature. Now let us switch over to the next page and solve forward. Now we know, since we've been asked for PQ, we'll only be considering PQ. So this is P, this is Q. Let us consider also, we know that the junction temperature, which was T now, is equal to 140 degrees centigrade. This is 10 degrees centigrade. Now let us take a small element of width dx and x distance from P. Now we know that this rod is 1 meter as is given in the question. Therefore, this portion will be 1 minus x. Also, we've studied in the temperature gradient part that the temperature gradient is same for any in the same material for any two parts. Temperature gradient is essentially delta T by distance between them. So now here we can see that 140 minus, let this junction temperature be T naught. 140 minus T naught, distance between them, which you'll see is 1 minus x, equals T naught minus 10 upon x. Now 140x, we'll proceed with the calculations. T naught minus 10 minus T naught plus 10x. Let us, I missed the x. This will cut. We'll send this over here. Transposing, we get 130x plus 10 equals T naught. Now we find the T naught. So essentially the question is, why did we even find the T naught? We found the T naught because firstly we need to integrate. Now let us say the element which we took at a distance x from P be dx, which we already assumed. Now the expansion we get, let that be dy. Now from the linear expansion of thermal materials, we get that delta L by L equals L naught equals alpha delta T. This is how we get the formula final length equals L naught 1 plus alpha delta T. So delta L in this situation we've assumed to be dy, so we'll take dy. Now L naught in this situation is dx. Alpha we've been given, alpha in the question is given as 1.2 into 10 to the power minus 5. So we'll keep it as that, 1.2 into 10 to the power minus 5. Now delta T clearly. So here we can see that in PQ this is 10 degrees centigrade, right? Because we're taking from P direction x. So Q is somewhere here, but we'll put that will come into the equation after we integrate it. So at a x distance from P, we have a 10 degrees centigrade at P. So the delta T will be the temperature here is, as we can see, the variable temperature with distance is 130x plus 10, which is T naught at any distance x. So at any distance x, the temperature is this. Hence 130x plus 10 minus 10. This 10 comes from this. So this, the temperature here, minus this temperature. Then we have put delta T, we have put alpha. Now it's simple integration. dy. Now let me remind you, we were asked the change in length of wire PQ, and the change in length of wire PQ will simply be an integration of dy. Now we'll send, since we know that this Leibniz notation is very flexible, we can absolutely send dx over here. So 1.2 into 10 to the power minus 5 into 130x dot dx integrated. Now from where to where do we have to actually integrate? So we have got to integrate from 0 to 1 since the length of the PQ is 1. First let us integrate. Now the integral of dy, let it be y, this is our required, equals 1.2, will bring the constant out of the integral material, x square by 2, and we have limits, so it's a definite integration in case you were wondering. 10 to the power minus 5 into 1 by 2 minus 0. Simple. So we get this 2 cancel out as 0.6. Now that's as simple as that. I missed the 130. If you don't remember, this 130 will be brought out of the equation since it is a constant material. Hence, so the 130 is brought out. 130 into 0.6 into 10 to the power minus 5 equals 13 into 6 into 10 to the power minus 5 meters equals 78 into 10 to the minus 5 meters. Therefore y equals 0.78 millimeters. That is the answer for this wonderful problem from our thermal chapter. Thank you.